Hello and welcome to everybody on Cloud Fitness. So in today's video, we are going to discuss about the mean squared error, mean absolute error, root mean squared error. So again, as I am explaining in my previous videos as well, there are few theoretical topics which are very important, because as we move to the hands-on session, the only change will be just one line, right? When I write a piece of code, right, it will be only one line of a change, but the theory behind that is very important to understand. So we need to understand what is this mean squared error, mean absolute error, roots mean square error, and when to use each of these, right? So let's move ahead, and before moving ahead, I do recommend all of you to connect with me on LinkedIn and Instagram, and I will leave the link in the description box as well. And if you are coming to my channel for the first time, I do recommend subscribing my channel as well. So when you talk about especially the linear regression, right, I'll start from there because that is the first algorithm that I actually explained what we are trying to find out, right? We have already discussed about this, that we are trying to find the best fit line. We are trying to find out y equal to mx plus c, right? That is what we are trying to find out. Now, what you see over here with the green dot is the actual value of y, and all the predicted value will lie on the line, right? That you try to develop as the part of your algorithm, right? Now, this is nothing but y and y dash, right? That is what we are trying to find out. That is your y is equals to mx plus c, and we want to minimize this error, right? Now, to minimize this error, we came across, we have understood, we have discussed about these functions. Now, to minimize the difference between y and y dash, right, to minimize the difference between the actual value and the estimated value, we came across this cost function which we have already discussed, right, which is nothing but 1 by 2m, the number of the data points, and then h theta x of I minus y of I of whole square, right? That is what we have discussed. Now, this is nothing but your cost function which we eventually have to reduce, right? That is what we need to reduce to get our best fit line. To get our best fit line, to get our y equal to mx plus c, which is nothing but theta 0 plus theta 1 into x, to get the best fit line, to get the best value of theta 0, right, to get the best value of theta 0 and theta 1, right, we have to make sure that we minimize this cost function. Now, if you closely look at this cost function, in fact, I explained this even in my linear regression video, that if you see, this is nothing but this is the square, right? We are trying to do a square, and here we are putting 2m, right? So this is nothing but the cost function. Now, when you talk about the cost function, eventually what we are trying to do in this cost function, we are trying to reduce it. When we say that we are trying to reduce it, we are, now when you plot this cost function, now all of these points I have already discussed. So when you are trying to plot this cost function, it gets plotted in this form, right, in this U shape, right? And we are actually trying to come to this global minima, right, this red dot. We are trying to come to this global minima where the gradient is 0, right? That is what our whole objective is. Now, why I am trying to tell you this? Now, eventually, the formula that you see, right, that is nothing but, that is a mean squared error formula, right, because you are squaring it. So, yi minus yi of hat, right? There are two ways of writing it. You can either say yi, basically the actual value minus predicted value squared, right? That is what you can write it like this, or you can also write it in this way that we discussed in our linear regression video. So I do recommend watching that video as well. Or you can write it this way, right? H theta x of I. This is nothing but the y hat, right? So you can write it in any of these ways. Now, if you see this 2 over here, so it is a squared, right, and you are dividing it 1 by n. So this is nothing but the mean squared error. So you are trying to reduce it. Now, similarly, there is something called as mean absolute error. Now, in case of absolute error, you are not trying to square it. You are just trying to get the modulus of it, right? You are not trying to do a square, you are just trying to get the modulus of it. Now, similarly, when you talk about root mean squared error, in that case, again, it is same as your mean squared error. You are just putting a root over here, right? This is the difference. Now, which one we should use and when we should use depends on few factors. Now, if you look at this mean squared error, now remember that for any kind of outliers, now let's say in case my value of y actual value is very huge, and my predicted value, there is a huge difference, there is a huge residual error between my y and y dash error, between my y and y dash, so that becomes my outlier. Now in that case I'm also doing a square, right? So what happens over here, it is going to increase that value, it is going to increase the effect of that particular outlier, which we might not want, right? So whenever we are using mean squared error, we should be cautious of it, that it cannot handle outliers, right? And also, let's say I am trying to predict height, right? Like let's say my height is in meter square, is in meter. Now the moment I do this square over here, you actually see my mean squared error becomes meter square because of the squared function. So eventually my predicted output is no more in meters, it is in meter square, right? So even the unit is squared. So do you want that or you don't want that? That highly depends, like based on that you can actually choose from mean squared error, mean absolute error, root mean squared error. Now similarly, if you go to mean absolute error, here there is no square, right? So the unit is not squared over here, and it can handle outliers because you're not squaring it, right? If you see over here y minus y hat of square, right, if the difference is 5, it becomes 25 over here, but that's not the case, it is not being squared at all, so it can handle your outliers. But when you talk about your root mean squared error, here also unit is not squared because you see it is root, right? So it gets divided by, this 2 gets divided by 1 by multiplied by 1 by 2, and 2 and 2 gets cancelled, right? So in this case your unit is not square and it can handle outliers as well, but there is more to it. Now when you talk about mean squared error, right, now whenever you want that if your large errors are there, and if you want to have an effect of those large errors on your output, then in that case you can use mean squared error, because mean squared error is actually giving more weight to outliers. Even if it is 5, it is making it as 25, right? So if you want such condition, go ahead and use mean squared error, right? And it is differentiable as well, so that is a very good plus point, that it is differentiable, right? Now you can actually get 2 over here, right? So it is differentiable. Now when you talk about mean absolute error, right, now in this case what happens is even outliers, right, they do not have much weight. So in case you want to make sure that, okay, even if I have a huge error residual, right, but I don't want to give it, too much of weightage, then in that case you can go for your mean absolute error, right? Because in mean absolute error, it will treat all your errors equally regardless of the magnitude, because here if magnitude is 5, it becomes 25, but that's not the case over here. Now similarly, when you talk about root mean squared error, right, now in this case if you want a more interpretable metric, basically over here unit is not squared, right? So it becomes more interpretable metric than your mean squared error, because here what happens over here, your unit is squared, but here your unit is not squared, but still you have more weight to the larger errors. But still here what will happen, if it is 5, it will still have more weightage over here, right? So that is what the difference is between mean squared and the root mean squared error. Now in this case, if you see, right, especially in the mean absolute error, optimization is bit complex and it is non-differentiable because it is modulus, right? But here if you see, root mean squared error is kind of used widely, because it is nothing but an extension of mean squared error, and it has best of both mean squared error as well as mean absolute error. So we use it a lot because even the unit part of it doesn't square the unit, but at the same time it gives weight to the large errors as well. So sometimes we also use mean absolute error and as well as root mean squared error. So this is very important to understand this concept, because that is when you will be able to implement it in theory. So I hope you like this particular video. Do remember to like, share and subscribe to my channel, and thank you so much for being till here.